Very good. So good afternoon or good morning, everybody, and welcome to this last virtual seminar on multi-messenger astronomy before our Christmas break. Today's speaker is Miguel Mustafa. He is professor at the University at the Pennsylvania State University, and he is an expert on very high energy gamma ray searches. And today he's gonna talk about the high altitude water Cherenkov Observatory, HAWC. And yes, so as usual, the talk is supposed to be around 50 minutes long, and at the end we will have our Q&A session. Feel free to, at the end of the talk, to use the raise hand button to ask your question, or if you don't want to ask it yourself, you can also write it down in the chat and then I will read it to Miguel. Okay, I think that's all. After this seminar, we will have the next one in January on the 13th of January. And yes, so we'll have almost a month of break, but then we will start stronger than ever. Okay, so Miguel, the stage is yours and you have around 50 minutes from now.
Thank you. And thank you very much for the invitation. No, thank you to Elisa that said that she wanted to skip my talk. She got other things to do more important than listening to me. So I'm perpetually offended now. And thank you all for coming despite this terrible weather. It's snowing a lot right here. So I hope not to get cut off in the middle of my talk. So I will tell you about HAWC, which is the high altitude water Cherenkov Observatory. We work in the very high energy gamma ray range. And this is, I like to start with this cover because this is a painting by one of my Mexican collaborators, a graduate student in Mexico. And this is what he saw about our experiment. And this is an actual picture of our experiment, if I get my mouse on the right spot. And as you can see, he's pretty good. So I've been giving these talks for about 10 years now, and we started with, this is what we're going to build. And you should feel lucky because today I'm gonna show you that we have already 5 years of data in our can. And so we have a lot of super interesting results that we can talk about. But luckily for you, I only get 50 minutes, so I'm gonna be short. So first of all, I will tell you a brief motivation of why we're interested in gamma rays at the highest energies of gamma rays. I will describe my observatory, and then I will give you a brief summary of the most recent results, of the most interesting recent results. And then at the end, I will tell you what's coming next in the near future, in the few years future, and what you can expect from us. Okay, so let's get started. I'm not gonna tell you, I see the list of people and you've seen the flux of cosmic rays as a function of energy. And you know that we are interested in finding and understanding the sources of the highest energy particles in the universe. So these ultra high energy cosmic rays. And at lower energy, measure these cosmic rays with exquisite detail. Let's see if I can get them out. Okay, so we've seen all these different species, but as you know, these are lower energies and these are all charged particles. So we have absolutely no idea where they are coming from, which is what we're interested in. So up to about the knee or below, somewhere there, we can do direct detection because of the flux level. So we have fluxes of particles per square meter per second. So if you put a detector of about a square meter, you can measure all these fluxes directly. If we want to go higher in energy, like we are trying to do, all these measurements are indirect. So what we see is not that primary particle. We see the shower that it's produced by the interaction of these cosmic particles with the atmosphere. That's why we call it indirect. So we can build bigger detectors, and that's why we can see these fluxes. So this is what we're interested in doing. About 20 something years ago, I got convinced that if we go and measure these highest energy particles in the universe, these are such high energies, and my theory friends told me that these were going to be protons. So we said at these energies, protons are going to come straight to our source, straight from the source to us. We're going to start doing astronomy with charged particles. This is going to be awesome, sources. So we built a detector to see this, and this flux is now, so once you get to this area here, we're talking about 1 cosmic ray per square kilometer per century. So either you're very patient or you build something really big. And that's what we did. About 20 years ago, we built the Piaget Observatory, which is 3,000 square kilometers, a particle detector every 1.5 kilometers. So triangular grid of 1,600 detectors covering 3,000 square kilometers. You could say, well, how big is 3,000 square kilometers? So this is the famous Large Hadron Collider that they call it large. I don't know why they call it large, but this is the ring of the LHC, where it is in Geneva, and these are 3,000 square kilometers. So all this area is covered with particle detectors every 1.5 kilometers, everything here. If you've never been to Geneva, I think that this is where you are right now. I've never been there, but I've never been to Geneva, but I've been to Garching, so I don't know where you live, but I know that the institute is somewhere here. So this whole area, everywhere inside this red line, every 1.5 kilometers, there's a particle detector. That's 3,000 square kilometers. That's huge, amazing. Okay, so we run this huge detector for 20 years. And this is the most anisotropic map of the sky in cosmic rays at these energies. The colors are, it looks like a big dipole, but the difference between hot and cold is 5%. So this is a 5% dipole in the sky. Still the cover of science, well, not the cover, it still make it to science, but no sources. They're either heavier than protons, or the magnetic fields were larger than what we expected. For whatever reasons, we don't find point sources in cosmic rays, even at the highest energies. So that's why I decided to move on to gamma rays. So about 10 years ago, I started working on the HAWC collaboration. Look at this beautiful map in GeV. This map is from Fermi, of course. And you see the plane of the galaxy, and you see all these point sources everywhere in the sky because photons come straight to you. So that's as high in energy as Fermi can go, but we can go higher in energy using ground detectors. So for example, this is a TeV gamma ray source seen by HESS. So I will tell you about the different types of experiment in a minute. But the idea is that, okay, so you see these sources, but they are gamma rays. So how are these gamma rays produced? And so they could be accelerated by 2 different mechanisms. They could come from electrons, electronic origin, in which the electrons upscatter photons of lower energy. So some kind of inverse Compton scattering, and they give you the gamma rays. Or we could be talking about protons that interact with the environment in the source. They produce pions. 1/3 of those are going to be pi zeros, and that give you, again, gamma rays. Either way, the morphology, because if you're talking about a leptonic origin, you still have synchrotron emission at lower energy. So the morphology of the whole energy range, if you look at the X-rays, the morphology matches the morphology at TeV. That gives you a hint. But you also need to look at the distribution in energy. So you look at the morphology of the source, you look at the spectrum of the different sources, and you try to figure out what is the mechanism. Either way, you're finding electrons or protons of higher energy. If you get TeV gamma rays, you have to have higher energy electrons or have high energy protons. So that's giving you the sources of those cosmic rays up to those energies. So this is what I was talking about, the morphology. You're trying to match what you see, for example, in X-rays. Those are the contours that you have in here, what you see at TeV in the colors, and you're trying to match the energy spectrum in the synchrotron region with the TeV. So if you measure in the highest energy, in what we call very high energy range, TeVs, you'll see that you could have some discriminating power between the different models. This is the same source fitted with two different physical models of the source. So in conclusion, that's the, in a 2 minutes elevator speech kind of thing. Motivation why we're interested in doing very high energy gamma rays. If you look at if you can measure the spectrum of a gamma ray source up to say 100 TeV, that it hasn't been done before, you can build a deceleration of protons up to a PeV. So trying to find these famous pevatrons, whatever they are. And the advantage of having a detector that can see a very large patch of the sky basically all the time. So with a high duty factor that it's looking, even if it's snowing outside or if it's at night, the detector is taking data constantly of a very large part of the sky. So you are gonna find things that you weren't expecting. And that's the main motivation to build a detector of this type, which I will tell you right now. So how do we detect gamma rays? So as I told you, they have the direct detection. So for example, you have a satellite experiment like Fermi, as this cartoon, and it has a great advantage, which is they see directly those gamma rays and cosmic rays. So they can see, I detected a charged particle, so that's background, I don't want it. That's very clear, very easy to do. The disadvantage is that that's as large as you can put on space. So Fermi is as large as you can do, and therefore you can't go much higher than what they do, which is a few hundred of GeVs at the most. So if you want to go to higher energy, you have to come down to the ground. So there are different types of detectors on the ground. One of them is looking at atmospheric Cherenkov. So this is looking at the Cherenkov light produced by the showers in the atmosphere. So these are telescopes. That means that they operate during the night. They have a very special conditions on the weather and so on. So the duty cycle, it's low, but on the other side, they are telescopes. So they have an exquisite precision, not only in the angular resolution, also in the energy resolution. So you have a very precise instrument that works only a short amount of time, and you have to point. The other possibility is to put on the ground particle detectors of any kind of particle detectors that you can think of, and you can make it as large as you want, and they work all the time, basically. So you can build it as large as they give you money, and they work all the time. That's the great advantage. Obviously, well, I would say that is, to me, in my mind, and many people in the field would disagree, there is really no competition between the different kinds of detectors, because the low energy part is covered by Fermi, and in the high energy region, the two types of detectors have very, very different features that make them perfectly complementary. You can have it that tells you, look, we weren't expecting emission from this particular region. There's something going on. Why don't you point your telescopes to that? And they can have a description of that particular area with a level of detail that we can never do with the other type of detectors. So the level of complementarity, I think that is perfect. So this was a picture of Milagro. That was a very large water Cherenkov-based detector, and that's what we use to build HAWC upon. So we use the experience from the Milagro experiment. That's why we call HAWC a second generation water Cherenkov detector. It has a very large instantaneous field of view. The 2-star radiance come from the 45-degree angle that we use. So anything within a 45-degree cone in the sky, it's our instantaneous field of view. So we see, after the whole day, we see 2/3 of the whole sky. It basically operates all the time. We are down if the Mexican electricity company shuts us down for some unknown reason. So very, very rarely. And we covered about 22,000 square meters. And that's when we ran out of money. So this is the detector that we built at 4,100 meters. And based on what we knew from Milagro and based on what we do now, the main motivations and features of this type of experiment is that we are good for extended sources. And we've seen already with Milagro that a lot of the GeV sources from Fermi continue into the TeV range that we see with Milagro already. And this particular type of detector is very good for extended sources and sources with a hard spectrum. So extended sources mean, I will show you what we see so far, sources that are really too large to see with a telescope that has a field of view that is comparable or even smaller than the size of the source that we are looking at. So this is what we designed, 300 tanks. We call them particle detectors, but they are water tanks. Each one has 4 PMTs at, like I said, 14,000 feet, if you like feet, otherwise 4,000 meters above sea level. And this is what we actually built. These are the 300 tanks. Each one is 7 meters in diameter by 5 meters tall. And these are what the tanks look like. If you want to compare, if you heard about, I told you about HAWC before, these are the water tanks that we deployed in Argentina for HAWC. And these are the tanks in HAWC, which are 5 meters tall and 7 meters in diameter. Each one has a bladder inside, which makes it light tight, and is the one that is holding the water inside the tank. And this is how they work. As I told you, they have 4 PMTs inside. So we see that Cherenkov light produced from these relativistic secondary particles in the air showers. 3 of those PMTs were from Milagro. We are reusing those PMTs. That save us quite some money. They are 8-inch PMTs, and the central one, those are new. These are 10-inch high quantum efficiency photomultiplier tubes. We have a dedicated calibration system that I'm not going to spend a lot of time on this part, but if you're interested, we can talk about it. So we use a laser. We have a single laser. We split the light in different fibers. Those are the ones that you see in the picture here. And we only have one of these. This wasn't a prototype that we were playing with these kind of things. That's why there was a camera inside. And you can see how you can use the float from your toilet to make a scientific instrument. And we use the light from the laser to calibrate our signals, both in charge and in time. We have a filter, so we have like a 4 orders of magnitude dynamic range in the signal size. And this is an uncalibrated piece of data pointing to the direction of the moon. So without any cut, so this is not gamma rays, this is cosmic rays. And you should see the moon, but we don't see it because this is uncalibrated data. So if you use your laser and you calibrate both in signal, so the amount of charge, and in time, this is what you get instead. And that's the moon. And right before you raise your hand, yes, the moon is round, and this is only a couple of months of low energy data. So that's why it looks like this. If you look at this map with a decent amount of data, that's your moon, and now it's round. And I said it before they raise their hands, but that usually happens in a live talk. So this helps you not only realize that your calibration is working, but then you're pointing because it has to be shifted. The size goes with the angular resolution, the median energy of the deflection of the cosmic rays, and that's why it's not in the same spot. So this helps you a lot for the verification. So that was one of the first measurements. We discovered the moon. So in conclusion, this is the detector. This is what it looks like. Each one of these circles is a tank. And I will show you a shower. So the timing you will see and the colors give you the charge. So this is how a gamma ray shower looks like in our detector. And you'll see going down. So you see the timing distribution that gives you the direction. And then by the charge, you know where the core location is. So that's how you do the geometrical reconstruction of each shower. The location is in Mexico. This is the HAWC site, which is about 4 hours from Mexico City, 2 from Puebla, another 2.5 from Veracruz, depending who's driving. And this is a aerial picture. This is where we were planning on doing. That's why the Photoshop has it over there. This is where we actually built it. So this is a picture taken from an airplane. That's why it's not super great. This is Pico de Orizaba, the 3rd tallest peak in North America. This is the large millimeter telescope, which is about 500 meters higher than HAWC. This is what it looked like 10 years ago before we started. And this is what it looked like when we finished construction in 2015. This is the inauguration in 2015. And you can see big trucks right here, and you can see people walking around our big tanks. So this is a very busy plot, and it always gets you in trouble with the other experiments. So I'm gonna make my points in here. We designed this detector to be more than an order of magnitude more sensitive than the previous detector of this kind, the Milagro experiment. We succeeded in that. And we designed it to have a very similar sensitivity than Fermi has at 1 GeV. We wanted a similar sensitivity at 1 TeV. And that's what we did. The rest is details that are not important to my points here. Okay, so this is the map of Fermi again, but only for the highest energies. This is what I call the Fermi smile. And this is the plane of the galaxy. So now I'm going back to equatorial coordinates. So it looks like a smile. And this is what we see with HAWC just after 1 year of data. This is above a TeV data. And if you superimpose, you see how I was talking about the continuation from what we measured at GeV all the way to TeV. So that's what we wanted to see, and that's what we're doing. Okay, so this is the first half of everything I wanted to say. This is my detector. This is my motivation. This is the instantaneous field of view. So again, everything that we do, the best features are that we work all the time. So we don't work all the time. The detector takes data all the time, and we have a very large instantaneous field of view. So each one of those maps is like 10 minutes of data. So those are photons in individual pixels every 10 minutes, each picture. So you can see what we do all the time. So based on this I'm going to tell you right now, which are the most recent results and what we are planning on doing next. I usually stop for questions about the detector, but I think we'll do it all at the end. So write them down. Okay, so let's talk about science. And when you go to Rome, you do as the Romans, but we go to Mexico. So one of the first things that we did with the first catalog, which you had about 1.5 years of data, we did a blind scan of the sky within our field of view, and we found sources. So without consulting with anybody, we get 40 sources, and about a dozen or so were sources that haven't seen before in TeV. So this is what we call unidentified sources. And before you get scared and before you go away, I'm not going to go through 40 sources, and I'm not going to go through the 12 unidentified sources. I'm going to show you just 2 or 3 of the interesting spots. Okay, so let's go to the first part. So this region is very interesting in the galactic plane, like between 52 and 55 degrees in longitude, galactic longitude. And we see three sources in this region, like you see here in these points. The first one was right on top of a source that was discovered by Veritas, and it was seen by HAWC. It's coincident with a supernova remnant. There's a pulsar right there. It's this location here. This map on the right is in equatorial coordinates, and this is from our paper together with Veritas and Fermi. So the colors here in this map are from Veritas. The contours kind of match our map, so they should match the map on the left. The white contours are the HAWC regions, and so this source is associated with this pulsar, at least spatial coincidence with that source. The next source that we see is this one here. This is one of those new sources. Unfortunately for us, and that's why you had the star when we published this so-called second catalog, there is no 2 sigma separation between these two peaks. As I told you, this was a blind search. So we ran a blind search over the sky and we said, anything that is above 5 sigma, it's a candidate. But if between those two bigger than 5 sigma peaks, there is no valley or more than a 2 sigma separation, we are not sure if this is a contribution from a bigger source or what. We can't tell them apart. In any case, as you can see here, this is the region of that source. There is a 4 FGL now source that is like about 0.1, 0.2 degrees away. The spectra don't match, and Veritas doesn't see anything from that source. So we're not so sure about what's going on in there. A much more interesting one is about a degree from that first source, and it's right here. It's the brightest for us. And as you can see on the right, Veritas does not see it. None of the ISCTs see this source. There is a Fermi source right there. It's on top of it's coincident with the pulsar. And Veritas not only doesn't see, it has a very tight constraint on a point source. So all these combined says, if we get more data and we can claim that there is something there, it has to be an extended source. And in fact, we see it extended. So like I said, this 2 HAWC catalog was about a year and a half. We now have 5 years of data. So this is a map from some of my undergrads working on this. So this is just to show you what we are doing right now. So now we are trying to model this whole area because we do see this source very, very bright. So it has, and as you can see, it's an extended source. So we are modeling this as a point source because HAWC and Veritas see it as a point source, and that's part of the great complementarity between the two types of detectors. And we kind of see still the source in here. We also see that our emission extends to cover another Fermi source in that region. But as you can see, this is a very complicated region. So we are trying to do a multi-source morphology fit of this area right now. And this is work in progress with the most recent data. So let's move on to another region closer to the Cygnus region here. We have also this unidentified source in here. And just like the other ones, the other experiments went and looked. Veritas had some little excess previously there with their archival data, so they decided to look further, and they have a source right there, so they confirm it, and this was one of the new TeV sources discovered by HAWC, and this is the map from Veritas, so these are the excess from Veritas. Our initial location was on this blue cross. The diamond is the location from Veritas. And as you can see, it's very clear. We have another source in here that they don't see. And this is a paper down there where you can have this source, and the previous plot is also from this paper. So once you master publishing a paper in a very large collaboration, you can practice doing 2 and 3 large collaborations. It's a lot of fun. I highly recommend it. This is our current map of this region with 5 years. So as you can see, our big excess here is moving right on top of Veritas. So the next analysis of this area is going to be very exciting, because now we're looking at the spectrum of this source. And as you can see, we still see some emission in this area here, where Veritas might be seeing something there, I don't know. But so this is work in progress too. If I move to the Cygnus region now, there is also a new source, an identified source in this region here. There was nothing there previously, known pulsars or known supernova remnants there, and no Fermi sources. Fermi had at some point some 4 sigma excess in that region from actually two places here, if you see those contours. So we started looking at the most recent Fermi data, and now we have hardware analysis matches perfectly what we see with Fermi. So we have a very recent paper on this new source discovered by HAWC, and the morphology is very similar. We see an extended source of about 0.8 degrees, both in TeV and in GeV. The cyan here is the Fermi-Lat analysis. The spectra of the two also match, and they show some steepening of the flux at our energy range. So now we have more data than when we published this paper, and we're looking into the energy bands to study this. So far, we cannot tell if this is a hadronic or leptonic, and we're still looking to even lower energy data and trying to find what object is the one responsible for this emission. So these are all, like I said, these are only a handful of places that I picked where we have some interesting results. Yesterday, so the slides that I sent you, Kiera, doesn't have that particular reference because it wasn't working yesterday. It was accepted for publication yesterday. So I just added it today, 5 minutes ago. So the third catalog is now out. The third catalog has the 5 years of data, 1,500 days of HAWC data. And not only we have the paper out, we also have this public data set. So you can go to our website. The link is there at the bottom. Subscribe and like, whatever. And you can go and play with that data there. But everything that we've done with these unidentified sources, some of them disappear, so they don't make it to the Phi Sigma. There are new Phi Sigma excesses in our blind search. This is a blind search independent of the other one. Of course, it contains that other data, but again, there's a lot of fun to be had with this map. Okay, so let's go back to the old data. And the other feature that I told you is that we can see extended sources. So one of those examples are these two pulsars that are nearby. They are in this region near the crab, and Geminga, and this other pulsar B656 plus 14. And intentionally here you have the moon, so for scale. So this is what I mean when I say extended source. So this is how you see the moon. This is how we see Geminga in TeV. So that's extended, all right? So the analysis of these sources are very interesting, because there's this excess in positrons that Pamela discovered and that AMS sees very clearly. And of course, just like, people on particle physics used to see bumps and they used to see Higgs everywhere. Whenever we see bumps or anything unexpected, is dark matter for us. So one of the possibilities of this positron excess is dark matter production, but the nearby pulsars could be an astrophysical source of these excess of positrons that we see on Earth. So that's why it's interesting to look at what we can see. So we look at what we see again, the spatial distribution, the spectrum that we measure, and try to see if we can explain the production of positrons that will reach us from these pulsars. So we measure the source, we look at this emission, and we can measure the surface brightness as a function of the radial distance, so the distance in the source. We know the distance to that source. So this is about tens of parsecs inside, and we look at that brightness, and then applying some assumptions, so that's where your theoretical prejudice comes in, you can predict what is the flux of positrons that you expect on Earth. And so with our measurement and with the assumptions that we have in the paper, that you will have to go and read the paper because I'm running out of time. This is our prediction for the expected flux produced by these two pulsars, the positrons that will reach Earth. And this is, the green one is the measurements from AMS. So as you can see, we have room for other sources, not just dark matter, but also dark matter, to produce these positrons. Again, let me try to make the message pretty clear. This is the combination of two things. And then you can argue very reasonably that if you use your own model to predict the positron flux, you might come up with something much closer, even though even the shape is very different to explain something that looks flat. But regardless, you could say, well, that's because that's when it goes down. Anyway, my main point, the thing that I want you to get is that we, HAWC, we can measure sources that are 5 degrees in the sky, which is extremely hard to do with telescopes. In fact, when we tell the IACTs to go and look in that region, for them it's very hard because the telescope field of view is comparable to the size of the source. So it's very hard to measure a source like that. If you ever look through a telescope, you know what I'm talking about. So that's the main point that I want you to get. Don't get stuck in, can we rule out or not dark matter? Okay, so speaking of extended sources, this is 1908, a source that Milagros saw and that we also see at TeVs. What we've done in this region is we've taken out, and you'll see why, we subtracted, we modeled this semicircle here, and we subtracted 1908. And when we do that, we end up with this TeV emission that matches the jets of this microquasar SS433. So the contours here, these black lines, are the X-ray contours. And you can see the two jets that are almost perpendicular to the field of view. So we see TeV emission from both jets and not from the central engine that produces the jets. So this is factors of 3 of 10 higher energy in gamma that anybody has seen from a microquasar. And this is our first measurement. We only have about 1,000 days when we did this measurement. So our measurement is at a fixed 20 TeV. We couldn't do a full spectrum of this particular source, but this is extremely interesting because our measurements here can help us understand better the mechanisms of particle acceleration in jets. And microquasars, not only is the first time you can say, well, yeah, it's the first microquasar you see, who cares? But microquasars are scaled down models of the jet's acceleration in AGNs, for example, that we cannot resolve the jets of AGNs in TeV. So that's what's interesting about this. So again, with the most recent data set and with the energy analysis that I'm going to show you right now in the last 10 minutes that I have, we will have the spectrum of these two jets and we'll start understanding better these acceleration mechanisms in jets. So that's what is exciting about this. So everything that I show you so far is the analysis that we have in bins of size. And that's what you do in COVID times, right? That's what you have it in my screen and not there. So the first thing that we did years ago is the measurement of the crab. That was the spectrum of the crab. And we developed a measurement of the energy on an event by event basis. And so now we are doing the spectra of all these sources that we see in this way, in which you see these fluxes with points, data, instead of having a band that we said, well, all the data we have is between these energies, roughly to 68% confidence level or so. And so we'll give you the line. We'll give you our best fit to the spectrum. So now we have these data points. And as you can see, one of the big advantages is that we can have all this dynamic range at higher energy. Before, we have everything that we said, okay, anything that hits 85% of the array is the high energy part, but anything above 20 TeV will trigger that bin. So you couldn't have any dynamic range within that high energy bin, and now we do. That's the main point. So this is the PRL from the thesis of Kelly Malone, former graduate student here at Penn State. And we look at the sky at 56 TeV and 100 TeV. The 56 and 100 comes because we did quarter energy decades in log. So we did the same thing, just so the analysis is very conservative. We did the map of the sky in 56 TeV and 100 TeV, and we look for 5 sigma excesses in those at the location of known sources from our own catalog. So if we didn't have 5 sigma, we said we're not sure it reaches these energies. Anyway, so these are the maps of the crab. Sorry, I forget about my pointer. So this is the crab, and this is the galactic plane region here above 56 TeV, so higher than anybody else before. And I will show you, we have 9 sources above 56 TeV. Again, don't get scared. I'm only going to show you the 3 that go above 100 TeV. So this is this region of the sky. And this is all the data. So 1 TeV, roughly. This is 10 TeV. And this is 56 TeV. As you can see, this source here goes higher than 56, and it goes higher than 100. So this is the spectrum of this source, 1825. This source has 2 HAWC sources very close by. We can't tell them apart. That's I told you, the feature of an array. We don't have the angular resolution of a telescope. So there could be contributions from multiple sources in this spectrum that we have in here. Again, so what are we doing with all this? We're looking for pevatrons. So we're trying to see if you can find a source with a hard spectrum that continues without showing you any break in energy that will go further than 100 TeV. So it doesn't have much of a curvature. This is the region of 1908. So this is the map of 56 TeV, and this is the spectrum of this source. That's a source that was selected as one of the highest p-values in the IceCube search, blind search of galactic candidates. So that also makes it very interesting. This is the last region, so 10 TeV, 56 TeV, and this is the spectrum of 2019. As you can see, this one seems to have much more curvature than the other one, which is not what you want to see, but that's what it is. So this is the spectrum of all these sources. Right now, we can't really say if these are hadronic or leptonic. And so therefore, if they are really pevatrons, but we are studying it. Some of these regions are very complicated, so they could have contributions from other sources. So maybe, this that seems to be dying down, it could be 2 sources, one that has an energy cutoff and one that has a hard spectrum that continues going. So having more data will help us a lot. And not only we're looking at the new data set that I'm not going to show you because I'm being recorded. So, but we are also studying a multi-wavelength of all these sources. So we're trying to find what sources are in that region and trying to look for low energy emission to try to disentangle and come up with the actual emission mechanism. Okay, so I'm right on time. That's unbelievable. This is what we are doing now. we have, this is the main array, what we call the main array. All the results that I show you have been produced by data in this main array. And now we have deployed these little tanks, smaller tanks that cover a much larger area. We call them outriggers, and they are smaller. They look like this. So these are the HAWC tanks that I show you, and these are the outrigger tanks. And as you can see, they cover a much larger area. So we're getting a factor of 2 or 3 in sensitivity in the largest part. So above 10 TeV or so, we are getting a big boost in sensitivity, which is this super interesting part because we don't have that much competition. And this is very important because right now, so if you see this shower, this is an actual shower, it landed. So by the colors, you can see that the core of this shower was outside the main array. So right now, if we have a shower like this, well, not right now, last year, if we have a shower like this that landed outside, but still it triggered the whole array. So you have 1,200 points of data, but the core is outside. You have a complete ambiguity about the direction where it's coming from because you don't know where the core is. And worst, you have an ambiguity about the energy because if the core is very close to the array, it's an energy, but if the core is super far from the array, it's a much larger energy. So until recently, we couldn't use these events. And now with the outrigger array, we'll say, okay, the core is here. So now you can use the main array to reconstruct everything, the direction, the energy, very precisely. So that's what it not only give us a factor of 2 or 3 in sensitivity, it's a big boost in all these analyses that I show you so far. Okay, so that is coming very, very soon. And the other thing that is coming soon is that Hes told us that this was an interesting region. This is the galactic center. This is the colors are from Fermi. And this is our field of view with HAWC. So we barely reached that region. And this is very inclined showers for us. So we don't have a lot of sensitivity in this area. It'd be nice to see that region. Like I said, Hes says that it used to be a Pevatron at some point. So there might be some interesting sources in this side of the galaxy. So that's why we are working to build a HAWC-like detector, but in the southern hemisphere instead of in the northern hemisphere. So the field of view will be something like this with a little hole in the South Pole. And with this field of view, we'll see this part of the galaxy with a detector that works 24/7. And we will see structures like the Fermi bubbles completely, which, you know, again, if you try to look at the Fermi bubbles with a telescope, it's kind of hard. But if you have a large field of view experiment that covers all these regions, you have them completely, and you can study them as a function of energy. So it will be very interesting to build something just like HAWC, but in the southern hemisphere. Okay, so 11:50, let me finish. I told you about our scan of the galaxy. I didn't have time to tell you about transient sources. We have a couple of extragalactic sources, and the bottom plots here are looking at one of these 2 AGNs that we see, and the maps are 1-day data in the same part of the sky. So you see, this is the normal day of this source. The next day it looked like this, and then 2 days later it looks like this. So we do have transient sources. We do send circulars around when we see flashes in the TeV sky. But again, I didn't have time to show you all of this. I didn't have time to tell you about dark matter. We have a lot of papers about dark matter like everybody else. But again, one of the features is that we can see very large regions. So we can look at, so for example, if there's dark matter from big halos in our field of view, things like that could be interesting. I didn't say anything about cosmic rays. We have anisotropies and TeV cosmic rays. We have limits on the north Fermi bubble. What else I didn't say? I didn't say anything about low energy stuff because I don't care. I'm sorry if you do. Solar physics. I didn't tell you about EBL constraints. We found a new source, another pulsar this close to the crab. Everybody has been looking at the crab for ages. and no one saw this source because everybody took it out when they subtract the background for the crab. There's a source there, and because we don't need to subtract background from the same image, we found it. So this is another new source discovered by HAWC. We do a lot of multi-messenger studies. This is an event from subthreshold LIGO. So if you have only one interferometer, I'm not going to go into details, but you can ask me about it if you want. The location map of the sky of this one source is huge, but that matches our instantaneous field of view with HAWC. So not only we can do these single interferometer events, but LIGO come up with a new reconstruction of their events, and they go back over the old 3 data and they say, oh, we found all these new events that weren't before. I just go back into my data and I look for them. I don't need to point. I don't need to go run my telescope at that time. So we're doing a lot of other multi-messenger analysis that I don't have time to describe. And like I said, the future is bright. One day we'll come out of the house and we'll be using the outriggers to expand over our high energy part. That will be super exciting. And funding agencies willing, we will build a detector in the southern hemisphere, and we will do a lot of these cool physics in the other hemisphere. So that's about it. I'm 3 minutes too long. Sorry about that. Thank you for coming. Thank you for listening to me. But not Elisa. Everybody, but not Elisa. Okay. I'm ready for questions.
Thank you very much, Miguel. This was a really nice talk. And congratulations for the publication of the new catalog.
Thanks.
Okay, so time for questions. I saw, no, it was a clapping hand, I guess, not a raised hand.
Okay. Yeah, I was seeing hands. Me too.
Very good. So as I said, you can both use the raise hand button to ask your question or write it in the chat and I will read it. If you're a little bit shy, it's okay both ways. And while we wait for people to raise their hands, there's already a question by Ottavio Fornieri. Go ahead, please.
Hello, hi Miguel. Thanks for the very informative talk. I have a question. I have a question that is certainly coming out of my ignorance, so I'm sorry if it is too stupid. But in the beginning, you said that scanning the TeV sky, you didn't consult any other collaborations for no, that's okay. No, the point is, I'm still assuming that in order to discover a source, because you have a clear threshold at 5 sigma to call it a source, in order to discover a source, you have to subtract the diffuse component coming, for example, from the inverse Compton, because of course there are observations, strict observations on the gas mapping, but not for the inverse Compton models. And coming from this question, you also mentioned that there is one specific source that HAWC sees and Veritas doesn't. Is it possible that this come from this from two different inverse Compton models? Thanks.
All right, thank you for the question. That was awesome. Okay, so let me clarify first and then I go to your question.
Sure.
So what I meant by not consulting was that it is truly a blind search, right? So we didn't want to be predisposed from previous knowledge. And so we didn't say, okay, there are sources here, there, that, let's not look there or whatever. So we have, our data is 2/3 of the sky. We just grab our data and we did the blind search on that data. That's what I meant. And if it passes that 5 sigma, we don't call it a source, just for all the reasons that you mentioned. We said that's a candidate because, it's a 5 sigma. So it is a candidate. And it happens that we already have discoveries out of those 5 sigmas. we did that with the 1.5 year data. Now we have the 5-year data. So now we keep following those little phi sigma, and they have to continue growing with time if it's a real source. So now we have a handful of unidentified sources, and these are very strong candidates because not only they pass the phi sigma in 1.5 years, they continue growing with the 5-year data. So those are very strong candidates. Now, like you said, this map has, we subtract what we call background, but it's an empirical subtraction. It's not the very involved, you know, Fermi style model where you put your diffuse emission map where you take clouds or whatever, and then you have your model, and then you take that. No, we subtract the level of background in our data because, again, it's an indirect measurement. So we select, we reject everything that looks like cosmic rays, but it has an efficiency. So you know that you have cosmic rays in your data and you're cutting gamma rays too, because it's an efficiency and in a rejection efficiency, right? So in many of these cases, there is contribution from either multiple sources that we cannot discriminate, and there can be certainly diffuse emission that we are not taking out. So not only, well, it will be very hard to fake a point source with diffuse emission, but what certainly does is makes worse your spectrum measurement. So in many of these cases, we measure a spectrum that is higher than what the Cherenkov telescope see. And one of the main suspicions is exactly what you're saying, is like we are not taking into account some diffuse emission that they are subtracting the way that they are subtracting background.
Okay.
Like now, I forgot if I answer you to your question completely or not.
Yeah, you did. Thank you very much.
All right.
Okay, we have another raised hand from Dennis.
Miguel, thanks again for a nice talk. So I have a question relates to one of. Do you have any recent progress on the topic? I didn't follow it in many details. I just remember some paper some years ago that you have just an upper limit on Fermi bubble. So is there any progress in that direction? That's one question. And another related, is analysis of Fermi bubble simple for HAWC? Or size of Fermi bubble is still comparable to the field of view?
So I don't know if it's my connection, but it was cut off a little bit. So you're asking about the Fermi bubbles, right?
Yes.
So we only have, I think we published only one paper some time ago, and we put some limits, and our limits are not super constraining. So we keep following up, but I don't think that we can have, so let me put it this way. The low energy part of HAWC, so by a low energy for us, it's below a TeV. Below a TeV, we are not doing great. And that's one of the main improvements that personally I'm very interested in doing for the Southern Observatory. We need to make progress in our sensitivity at low energy because we're not doing great. And it's not easy because with these type of detectors, the footprint of low energy showers is very small. And so you have a lot of stuff triggering your detectors constantly. So it's not simple. And that's why we're not doing great at low energy. And that's why I don't think that you will see much from Fermi bubbles from HAWC.
Okay, thanks.
All right, another question from Andrea.
Hello, this is Andrea Sant'Angelo, actually from the University of Tübingen. Elisa sent us a very last minute email. I said, okay, another conference today, another talk. Then I say, Miguel Mostafa is talking. I said, oh, but that's a good occasion then to listen to a good talk and get updated with HAWC. And I was right. So I was right. It's
Grazie.
so the question is actually a series of questions. I will ask one which is really curiosity. Maybe I should read the paper. Okay. But you say here, searching for dark matter substructure with HAWC. So the question is very simple. What type of analysis you did? How could you distinguish this from, sources unidentified or whatever? And what type of candidates did you investigate, particle candidates, if any, WIMPs or whatever? So a brief summary of dark matter.
I'm not the best person to give you an update of dark matter.
No, not in general. What HAWC did.
That's not, but yes. So we did searches. Yes, they're all WIMP searches. But basically, it's looking at potential candidates where there is no TeV emission from a known source. So we're looking at places that are candidates, but are not TeV emitters of any other kind. So if you see emission, there's no astrophysical source that is doing it. So that most of our limits are coming from sources like that. And what I was saying that to me, again, because I'm not super interested in dark matter particularly, is that, everybody's looking for these decays anyway. What would make HAWC interesting? And to me, what is interesting is these particular spots that some people say that it could be dark matter emission from large halos. So if they are a few degrees in size or more, then HAWC could be a unique way of looking for TeV emission from these particular regions.
So, but then Miguel, if I have, so some unidentified or unknown source that you discussed about this today, these won't be candidate for dark matter spot.
That's right. No.
Because they are too small. Okay.
Yeah. No. Yeah.
Okay. I think Andrea raised his hands again, just right now.
I have a second question. But if there is someone else, of course I will.
No, please go ahead.
No, go for it.
Okay. So the second question, actually I have two questions. You said for this very fascinating, sources which are emitting up to maybe beyond 100 TeV, maybe those are really Pevatron or whatever, we will conduct also multi-wavelength observations at other wavelength. But, if I think to the resolution of the X-rays, take whatever you like, XMM, Chandra, whatever, or even lower energies, you will find plenty of sources. So how could you match those observations? It's the usual problem. And the second question is a bit provocative. You never mentioned LASO. Do you not consider it a competitor? I'm old enough to ask a provocative question.
Good for you. Good for you. I'm old enough that doesn't provoke me. So the first one is an excellent question. The second because one. It has to be. No, the second. It has to be. You're putting in some of your prejudice there too, because then you say, okay, let's look at the high E dot pulsars. We happen to have a high E dot pulsar on top of each one of these sources. That's, again, provocative. And so then you're talking about going and looking for the X-ray of these particular pulsars and see if that matches your physical description of the spectrum. The other thing that you could do is, we have regions in which, like I said, there are 2 HAWC sources right on that spot. So very likely that is not, what we are measuring is not from a single source. But then, HAWC can discriminate the 2 sources up to their highest energies. If they decay enough time, they could tell them apart. And so then they come and they tell you, look, there is a point source here, and this is the spectrum that we measure, and there's a source here, and this is the spectrum that we measure. And so you go with that model, and then you reanalyze your data, putting that prior in. So that makes a big difference too. So those are the kind of games that we are playing. Like you said, it's not trivial. And yeah, and so the other one, yes. So yes, LASSO is there too. And now they showed the other day that they see high energy emission up to PeV emission of gammas. We can discuss all day. We have all these discussions in HAWC for years. With these type of detectors, it's very hard to come and tell me, look, I have one event here and it looks like a photon. Yeah, but it looks like a photon. It's 80% probability that it's a photon. That doesn't make it a photon. We can talk forever about this. But the important part is, like, if you look in our catalog, the 10 brightest source in our catalog, 8 of those go all the way to 56 TeV, at least. So it looks like these sources keep going. They're not cutting off like we thought 10 years ago, that they're not gonna continue. You're gonna see maybe a handful of sources total. Most of these sources keep going. That's super interesting. So having LASSO is great. By the time LASSO is complete, we'll have our Southern Observatory that LASSO cannot see the galactic center.
If the agencies agree. In the COVID time. I mean, Miguel, anything is possible.
Yes. Absolutely. Thank you.
Okay, so thank you everybody for contributing to this Q&A session with Miguel. And thank you again. I guess we are really late this time, so maybe we should stop the meeting here. I thank you again. Yes, we plan to go also for a third series of this virtual seminar, so I cannot promise that I won't bother you again, asking you to come again here and giving another talk. Maybe you can go in more details about the
absolutely
that you showed in your conclusion slide, for example.
I can talk about Amon if you want. I can talk about Amon and tell you about Multimessenger, what we're doing here at Penn State.
I think we would all be very interested in another talk by you. So yes, thank you. And thank you, everybody. We see each other again on the 13th of January with a talk by Anna Nelles, who's gonna talk about, let me check because I don't remember anymore, my bad, software for large astroparticle physics project. And she's gonna make the example of radio detection of neutrinos. So be there and have a very nice Christmas, everybody, and stay healthy. Ciao.